Okay, so let's talk about not precisely about rational geometry. I believe that's what it's called. Rational geometry.
Rational trigonometry is what I call it. Yeah.
So let's talk about rational trigonometry. Not it itself, but actually what led you to that. So you have this knack, it's a strange knack, of saying strange in a positive sense, to look at what is so elementary, what's been looked at 1,000 times to the point now it becomes overlooked, and say, well, what is really going on here? That's a phrase that you've used. What is really going on here? In fact, you say that that's a great phrase to keep as a mantra as a PhD student to understand your PhD. What is really going on here? Now, see, for me, if I was to look at something as quote unquote simple as the circle, I would get so bored and I would move on. However, you don't have that. You're wondering what the heck is going on here. So please describe to me psychologically, where does that come from, and then what insights have you gleaned from investigating what ordinarily is seen as overtrodden ground without any new territory to explore?
Okay, so let me answer that in a sort of a retrospective way. I mean, the actual way that I stumbled upon rational trigonometry was somehow a sequence of accidents, and maybe that's not so interesting. But in retrospect, I could say that one can be motivated by the desire for generalization and generality and sort of universal applicability. So after Descartes' Cartesian revolution in geometry, we've adopted this very Cartesian point of view where numbers and everything, it depends on a prior number system. And so the usual assumption is that, okay, it's the real number system, or perhaps from my point of view, the rational number system. But if you're a modern physicist, you probably want to entertain the possibility of other number systems, like maybe even finite number systems, right? Maybe the universe is some finite automata with some vast number of but finite pieces, in which case it might be that a finite field is actually a more appropriate sort of underlying number and system in which to model things. So what can what we can aspire to then is to try to create a geometry which is so flexible that it will work in different systems, that it doesn't depend on having a particular underlying number system. And more generally, that it works in such a way that it doesn't depend on a particular quadratic form. So, the properties of the Euclidean quadratic form, where the unit circle is a circle, versus, say, a relativistic quadratic form, like in Einstein's special theory, where a unit circle has a hyperbolic aspect. That difference should not perhaps be so important. We should aspire to having a theory of trigonometry that works just in the relativistic setting just as well as in the Euclidean setting. Now, I think it's fair to say that physicists have struggled with this because the current trigonometry is not well suited for relativistic applications. But one of the advantages in rational trigonometry is that you kind of zoom out and you see what's going on in a bigger way, and so you see that these are all just aspects of the same kind of thing, and you can basically deal with them sort of all at the same time if you set things up correctly. So you can work over a general field, and you can work with a general quadratic form, and you can do that right from the beginning if you set things up this way, and then you cover all these things at one blow. So it's just hugely more powerful, even though particular aspects of something or other that we might be used to in the Euclidean world might not appear because they're not general enough. So that's a big advantage. I would say that's like a key selling point to the rational trigonometry point of view. A somewhat more subtle advantage is that it also makes it easier to unite the affine and the projective stories. So in geometry, there's largely sort of two frames of thought. There's sort of an affine or vector space or linear algebra sort of point of view, and then there's a projective point of view. And with rational trigonometry orientation, you can adapt the affine story to the projective story much more easily. And then what's called hyperbolic geometry emerges as a natural consequence of the projective side of things. And that turns out actually to be quite closely connected with the Einstein-Minkowski kind of geometry. So that's good also.
What I was getting at, firstly, actually, what is the status of rational trigonometry? Is it a field that's flourishing? Is it primarily you working on it? Are you having a difficult time convincing your colleagues?
Oh, you look, it's primarily me and my students. It will, I'm sure it will take some time for people to slowly, come around. Partly also because I have other projects that I'm involved with. I'm involved with this algebraic calculus and these various other things. So I'm not sort of solely concentrating on promoting rational trigonometry and going around giving talks about how great it is. I've got other things to do. So yeah, I mean, eventually people will realize that it's very powerful, but it will take some time.
What I was getting at before was psychologically, what is it that makes you go into looking at Babylonian texts and what Archimedes thought? I don't know of any mathematician or any physicist that goes back that far. In fact, it's rare to find even a physicist outside of a tenured professor who's even looked at Newton's original works. You're never assigned a page of Newton. You're never assigned a page of Leibniz. So what is it that, as physicists and mathematicians, we just assume, okay, well, it's all been filtered and we're taught the best of it, so we don't need to go back to the sources. What's making you go back to the sources?
Well, first of all, I'd say I'm not alone at all in this. I think maybe as a mathematician, mathematicians are aware of a very broad history. Mathematics has been around for a long time. Astronomy in its early days was really sort of part of mathematics. The terms are almost synonymous. So we think of ourselves as having a 3,000 year history. And if you include the Babylonians, it's more like 4,000 years. And so there's actually quite a lot of mathematicians who are quite interested in aspects of the history of mathematics. So I don't think I'm unique at all in that regard. But with respect to Babylonian mathematics, I'm especially interested in that. Well, first of all, because my initial interest was with Plimpton 322 and the realization that with Daniel Mansfield that this was really essentially a trigonometric table, but sort of along the lines, something similar or akin to rational trigonometry in 1800 BC. But another really good reason to think about the Babylonians is because they had this absolutely remarkable numerical system. I've been talking a lot about numerical systems, right? So we actually have a lot of numerical systems floating around currently. We have integers, we have rational numbers, we have approximate decimal numbers, we have real numbers, etc. And for a computer programmer, and then there's also binary, kind of system. These different types of number systems are all probably best kept apart and separate, and then you have to build bridges between them. So it's really interesting to find out that the Babylonians 4,000 years ago had this other number system, this base 60 or sexagesimal system, which was in many ways more powerful than our systems. This is a sort of a mind-blowing fact. That even today, if you had to start from scratch and said, okay, we're going to do maths from scratch, let's decide which number system we're going to use. Should we use base 10? Should we use base 2? There would be a good argument to be made to use the Babylonian base 60. There would be a very good argument to be made. I'm not saying that would necessarily prevail, but it would be a very interesting discussion to have. And so it's completely fascinating to me that these people, so long ago, living under what we would consider very primitive conditions, had such an evolved mathematical numerical system. It's completely remarkable to me. So I think that's so intrinsically interesting. Besides the many other things that they did, I mean, that's just one aspect of their remarkable culture.
Can you give an example of the sexagesimal system being better than the base 10? Some
Yes,
non-trivial
there's a really good example to keep in mind. When you're learning fractions in school, and actually the relationship between fractions and decimals, you learn that most fractions have repeating decimals. That is, they're not finite decimals. But some fractions have finite decimals, like 1/4, that's 0.25, or 1/8. And in fact, the fractions with finite decimals are the ones with denominators whose factors are all 2s and 5s.
Oh, I didn't know that.
Yeah, so if you have a denominator and it's a product of some power of 2 and some power of 5, then that's going to be what we might say a regular number in our system. It's going to have a finite decimal. Now, the Babylonians basically did like a decimal arithmetic. They didn't deal with fractions. They dealt with decimals, but they were finite decimals. They had no infinite decimals. But in base 60, since 60 has factors 2, 3, and 5, there's crucially the factor 3 that gets added to the list for regular numbers in base 60. So if you're a Babylonian, any number that is made out of just 2s, 3s, and 5s, if that's in the denominator of your fraction, then you're going to be able to convert it to a finite decimal. That means something like 6, 1/6, 1/12, 1/18, 1/24. The number of numbers which are regular in your system is hugely more, and so you get a much more tractable arithmetic. So if you have to restrict yourself to finite decimals, that's very restrictive for us because we can't capture a lot of fractions that way. The Babylonians could capture a lot of fractions that way. So their sexagesimal sort of decimal arithmetic was demonstrably more powerful than ours for exactly that reason. And this they had tables for everything. So they had actually tables of the reciprocals of 1/6. What's that as a sexagesimal decimal? So they had lists of all their regular numbers, and these are things that all the scribes would have memorized. So this is a very concrete example of a powerful advantage to the base 60 system.
Is there a non-arithmetic example? Like, let's say we go all the way to complex. Is complex analysis affected by this?
Is complex analysis affected by this? That's a good question. I might have to think about that, but generally speaking, a lot of once you adopt a sensitivity to removing real numbers, okay, then questions like things like the square root of 2 or the cubed root of 7 or something have to be constructed algebraically if you want an exact theory. If you're an applied mathematician, you can still use square root of 2 equals 1.414, no problem. But if you want a sort of an exact algebraic system, you have to start constructing what we call extension fields for these radicals to live in. And so a lot of problems in geometry and also in other areas sort of meet this issue of whether a given number is a square or not. This is like a critical question. So can you take the square root of 7? What does that mean? It means, is there a number in your number system whose square is 7? So that's a number theoretical issue. Now that's not going to change if you change your base. Okay, but it will change if you change your number system. But so whether there's something like that with the Babylonian system in which the 60 manifests itself in terms of some number theoretical property, I'm not sure. But my guess would be yes, because actually there's a lot of number theoretical questions that are somehow base 10 oriented, but maybe they're not that interesting.